In the last recording, we went through Kirchoffs' first loop rule, applied it to a circuit, and it enabled us to calculate the current that flowed in that circuit. The thing about that previous example was that there was only one path that the current could possibly have taken. Therefore, one implication of that is there was only one possible current. Now we're going to step up the level of complication and have a circuit that has multiple possible paths that a current can take. And as you'll see, when I start describing it here, there's going to be more than one current for us to calculate. And so the math and the physics too get a bit more complicated. Actually, no, I tell a lie. The physics is actually simple. There's an additional amount of physics here. Kirchoffs' first loop rule was a statement about how conservation of energy is applied to a circuit path. The net change of potential when you traverse a closed circuit loop has to be zero. Close, the key point being there that the path that you traverse has to be a closed. You have to start and end at the same point within your circuit. So we talked about that, and it still applies here to this so-called multi-loop circuit. That's what this thing is called. Multi-loop circuits. Okay. So let's see how that plays out. We think about it the same way that we did for the single loop, which is you pick an arbitrary location within your circuit and you choose a direction to traverse a circuit. You write down the changes of potential that occur every time you encounter an electrical device, and then add all those changes of potential together and demand that sum be equal to zero. However, as you'll see in a moment, life gets a little bit more complicated. So with a multi-loop circuit. So once again, we'll pick an arbitrary point. I chose that point just because, why not? I could have started anywhere in the circuit. All right, so we're going to do the same thing. We're going to traverse the circuit, and a little more carefully now, I want you to imagine not just that you're sort of making your way mentally through the circuit, but in fact imagine an actual current flowing through a wire. That's going to be important. And remember, we're, as always, assuming a conventional current. Okay, I'm going to change my color coding here for reasons. There's nothing significant about that point A other than it's my reference point. Now, that way I'll know when I've returned back to my starting point. Okay, and arbitrarily, I guess this time I will traverse a circuit clockwise. And so, again, imagine actually a current I flowing. In fact, maybe I'll even say that. We have a current I that flows, let's say, out of this battery. And the current is flowing. It's still I right there. And we started from A. As we crossed the, first I'm just going to describe what happens, and then we'll do the equations after that. So we cross this battery. The current and the charges that make up the current go from a low potential to a high potential, thus they gain potential energy. We have an increase of potential. So there's that. So we have a plus V1. And then we make our way around. And now here comes the issue right here. And the issue here, and once again, I'm unhappy with my color coding choices. I apologize. The problem here is that when the current reaches this point in the circuit, this so-called branch point, now the question is, what direction, I'm sorry, which path of these two possible paths, which path does the current take? The answer is both of them. That is to say, some of the charges that make up this current I take the outside path, and the rest of them go through this central path, this inner path. Okay. How much goes in one path versus how much goes in the other path depends entirely on the resistance to flow that the charges that make up the current see for each path. And so, for example, if R1 here had an amount of resistance, if this was 10,000 ohms or something, and then R2 was 2 ohms, and then the resistance supplied by V2 was another 2 ohms, clearly the enormous resistance in the central path would make virtually all of the current take the outside path. On the other hand, if the resistance, the net total resistance is equal for both paths, then we'll get an equal amount of current that flows in each branch. Okay. I should be a little more careful, by the way. It's not just resistance, but rather the change of potential that he's going to experience, that the charges experience going through each path. That's what's going to determine how much current flows in each path. In any case, the point being that our current here, when it reaches this branch point, some fraction of it will take the outer path, some fraction of it will take the inner path, and that means, therefore, that in different parts of the circuit, we'll have different amounts of current. We've got a total current, I guess I'll call this a total current I in this part of the path, but on the outer path, we'll only get some fraction of the current, and in the inner path, we will get the other fraction, and it will go right through the resistors here. It's important, I'm going through this drawing carefully because it's important that you realize what the current is doing in each section of the circuit. And that's best realized and understood by color coding it in this way. A little closer. Okay. Now, the two subcurrents, let me label these more or less arbitrarily. In fact, completely arbitrarily. Let me label this subcurrent, I1, for no reason, other than I guess I called that resistor 1. And the other current I will label I2, arbitrary labels. And there's something else going on, which I'll tell you in a moment. But first, so I1 flows this way, I2 flows outwardly on the outside loop. And notice that like this, I1 plus I2 has to be equal to I. In fact, because I like doing this sort of thing, let's say I1 this is really going over the top even for me. I2, when you add those together, you get that total current. Look, I color-coded it. It's very exciting. Right. This, however, the reason I spent so much time doing this is this actually turns out to be the key to the whole problem. And in fact, this is the key physics right here, as I will now demonstrate. Because now let's ask the question, what happens at this branch point? Well, current I1 is flowing here, current I2 is flowing there. The two currents rejoin, add back together, and so the current that ends up flowing out of this branch point is the same as the current that went into this branch point. So this current, the total current I, reaches this branch point, split into two parts, and when they rejoin, of course, you get the same current back again. And we're back to current I once again. Now, where'd the physics happen? at the branch points specifically. Remember from early in the quarter that, or at least early in the conversation about electric charge, that the electric charge is conserved. Electric charge is conserved. You can't be created or destroyed. And in particular, in this application, that means whatever charge, and current is nothing but a bunch of moving charges, whatever charge goes into, more, or to speak it in terms of circuits now, whatever current goes into a branch point, that same amount of current must come back out of that branch point. Okay? That's conservation of charge. Whatever goes in has to come out because charge cannot disappear along the way. Charge does not disappear. Charge doesn't get used up as it goes through a resistor. The light bulb lights or the toaster runs or the laptop charges because the potential energy that the current is carrying gets lost. So the charges lose potential energy. That potential energy gets converted into whatever form of energy your device is using, thermal energy in the case of a toaster, for example, or a hairdryer. So the energy that the charges are carrying get lost to the resistors, but the charges themselves don't disappear. So the charges go in, they come back out, and there we are. This statement that the same amount of current comes out of a branch that goes into the branch is a statement of conservation of charge, as I just said, and it is Kirchoffs' second loop rule. To wit, Kirchoffs' second loop rule, the total current that goes into a circuit branch, as we call it, it must equal the total current that comes out of that branch. Kirchoffs' first loop rule is conservation of energy. Kirchoffs' second loop rule is conservation of charge. Now, no, that's enough for now. There's some more physics that I want to talk about, but small pieces at a time. So we'll stop here. In the next recording, I will make some points and clarify a few of these statements.